Hey everybody, welcome to Richmond Community College campus. We're here in Hamlet. My name is Sebrina Cropper and I'm a math faculty here, and I just want to take a moment and explain our math projects. So I have two trig classes, Math 172 and one Math 171 class Precalculus, and they are assigned to look outside of a math textbook and find a math problem. For Precalculus, they need to find a person, whether it's someone they know or maybe someone historically, and find a math problem that relates to them. For the trig classes, they need to find math in nature, and there are plenty of examples in nature, and display that problem, explain it, and we've got some videos of them doing so. Let's go ahead and take a look.
Hi, my name is Patrick Razon, and I am Sophia's father. I finished a bachelor's degree in electronics and communications engineering. Sophia asked me to do this video about the formula that I have learned from school if I apply it on my everyday work or in my everyday life. Anyway, the formula that we chose to use is the calculation of series of batteries. So in my job, I was a telecom engineer back in the Philippines, and we used to install radio repeaters. It's composed of multi-channel receivers and transmitters. So to power up those radios, you need a power supply, and you need a power supply that can compensate the output power of the transmitters and the receivers. Anyway, to compute that, what you have available are 12-volt batteries, car batteries. So if you have a power supply of 48 volts, anyway, by the way, the transmitters and receivers were powered by the power supply, which got a negative 48 volts. So since you have a 12-volt battery, you have to put a series of batteries to do that. So you put four 12-volt series batteries, and you add that, you get 48 volts. And Sophia should be able to show you the formula for it. I hope you guys learned something from me, and I hope I help you in on doing this video. Thank you.
Hello there, I'm Sophia Razon, and the person that you just saw before me is my father, Patrick Razon, and he is a former electric engineer, and English is not his first language, so I just thought that I should reiterate or summarize what he was trying to talk about with the series formula. So my dad explained to me that the series formula is a series of batteries all connecting from the negative to the positive charge to charge the circuit, or with a certain amount of volts in each battery that equals to the volts that's charging the circuits. And the example that he was talking about is the example I'm about to show you, and each battery, like I said, is connecting from the negative to positive charges, and each battery has 12 volts, which then equals up to 48 volts charging the circuit. And that's the series formula, and it's that simple. There's a lot more complicated math in his job, or what used to be his job, and he gave me something simple. I'm very thankful for that, because then I don't have to get confused. Okay, anyways, bye.
Hi, my name's Steven, and this is my math project for Math 171. My project is about a substation technician and the connection between math and it. there are many parts in a substation technician that rely on math. The person that I interviewed was Jared Lucky. Well, he is a part of the substation program. He's a teacher that graduated at RCC and worked in the field for 3 years as relay. And the connection between math and substation technician has a strong connection because technicians use the math formulas every day, such as linear and scientific notation. This is the table that they use on a day-to-day basis with converting resistors. And for example, this is the problem. A resistor has a value of 33k ohms. You'd want to turn the 33k into 3.3, the smallest that you could get it. So then you'd look at the table where it says K and it says 10 to the third. So then if it's a positive, you go to the left. So you move the decimal right here to the left 3 times, which would give you 33k. And this would be the value of the resistor.
Hi, my name is Ella Moore. Today I would like to talk to you about my Math People project. I chose to talk about Mr. Jerry Wayne Jones, the owner of the Dallas NFL football team. Back in 1989, Mr. Jones decided to purchase the Dallas Cowboy football team for $150 million. And today, the Dallas Cowboy team is worth $6.5 billion. That's a great percentage change. And how I had to come up with the great percentage change is I took and used the percentage change formula. I subtracted the $6.5 billion minus the $150 million purchase divided by the absolute value of $150 million, and I times that by 100%, and I came up with $6,350 million, and I took and divided it by 150 million, times that by 100%, and I came up with 42.3333%. And I took that and multiplied that by 100% in order to come up with my percentage change, which was 4,233.33%. Mr. Jones made a great investment over 32 years ago, back in 1989, when he decided to purchase the Dallas Cowboy football team for $150 million. That's my favorite team. I don't know who your favorite team is, but one thing I know, we will certainly meet you all in the playoffs. Thank you for listening, and you all have a wonderful day.
Hi, my name is Alyssa Roberts, and I'm going to talk to you about the Fibonacci sequence. The Fibonacci sequence is basically where you take the first 2 terms, add them together to get the third. Once you get the third term, you take back the second and the third, add those together to get the fourth, and this pattern continues. This can be represented by this equation, meaning that we're looking for whatever sequence number. We're going to take 1 away from it, add it to that same sequence number, but minus 2 instead. An example of this would be, what is the 12th number in the sequence? So we would write x to the 12th, since that's what the sequence we're looking for. And then you put x to 12 minus 1, meaning that we have to look 1 less than 12, and 12 minus 2, meaning we have to look 2 less than 12, which would simplify to the 11th sequence number and the 10th sequence number. Since we did not find the 11th earlier on this problem, we would take 21 and 34 and add those together to get 55. We'd plug that back in and grab 34 from our 10th number in the sequence, add 55 and 34 together, and that would give us 89. So now we're going to look at the golden spiral. Next thing I'm going to talk about is the golden spiral. The golden spiral represents the numbers in the sequence and how as the numbers in the sequence increase, when it is graphed, it represents a spiral formation as shown below. The golden spiral and Fibonacci sequence can be represented in nature in many different ways. For instance, the aloe plant and how it has a spiraling nature. The number of petals in a flower represent a number on the actual Fibonacci sequence, or even seashells and how they also have the spiraling effect. We can also look further away from just our visible things and do the hurricanes. From above, they also have the Fibonacci golden spiral. Even galaxies have the same type of spiraling.
I'm going to be talking about how bridge rectifiers work, how they're involved in nature. So basically, let's say your wall outlet, like how you charge your phone. 120 volts would go in. It would go through a transformer, and it would decrease the voltage to something that wouldn't make your phone explode. So then you'd have to convert that AC to DC, because obviously you can't really charge your phone with AC. The AC voltage goes in here. Since it goes back and forth, the dial's only allowed to go one way, so it'll only go this way and go this way, while on the other side it'll only go the other way, and so the other side comes out of this side. So, but because half of it cannot go through, you basically end up with a wave that just looks like this. This would be on a scale. So to fix that, you'd have to add capacitor and a resistor so that you don't have too much current to go through. And basically what happens is when that capacitor is charged, once that fall decreases, that capacitor basically will kick in right at the peak, and it'll slowly decrease until the next peak, which it'll go charge up again. Then once it goes back the other way, slowly decrease as you use its voltage, charge back up again, and it'll basically look like something like this. The higher the capacitance you have, the more straight the line is, as you have more voltage that takes up that space. And to do the math for it, to find this voltage, you'd basically take the volts AC, which is 112, and multiply it by the square root of 2, which would give you 158.39 volts peak. To find the secondary volt peak, you'd take the first number you got and you'd multiply it by the second number of the ratio, which would be 1, and divide it by the first number, which would be 5. And that'll give you 31.68 volts peak. To get the volts, the V out peak, you basically take that and divide it by 1.4. The reason you do that is because on this side, each of these take 0.7 volts away. Now, one of them is only allowing it to go through. That one will take 0.7 volts away as it passes through that. The other one, since one of them is blocking it, there's no voltage loss on that side. But on the other side, the one that goes through, it'll be another 0.7. So that'll be 1.4 you subtract, which would end up being 30.28 volts peak. And you assume the volts DC is volts peak. So the volts DC would also be 30.28. Now the current, you calculate the current of the output, you calculate by taking the volts DC that you just got and dividing it by the resistance. And that goes back to Ohm's law, which is volts equals resistance times current. To basically find the current, to find current, you'd have to divide the voltage by the resistance, which would give you 3.03 milliamps. Now the VR, you take that, multiply it by the time constant, which we're just assuming it's 8.33 milliseconds. You need an oscilloscope to read it. You take that, divided by the capacitance, which is 500 microohm, and then that would give you 50.48 millivolts. And then you have to solve for the actual output after that, which would be around here, and that would be the volt output minus the VR divided by 2, and that will give you 30.25 volts. So after all of that, you end up with 25 volts out back here. And this would be, let's say, a battery charger for something. And that's basically how it's connected to nature.
Hi, my name is Austin Morrow. And today we're going to talk about how to find the edge of the tree with math. This is our formula. We're going to take the circumference of the tree about 4.5 feet off the ground. We're going to divide that number, whatever it may be, by pi, and multiply it by the growth factor of the certain tree. The growth factor for the trees are different for every species of tree. This is a white ash tree, ASH. This is the tree we're going to use in our example today. So to find the circumference of the tree, you have to come up about 4.5 feet, which is about chest height on me. And we're going to be using a flexible tape measure. So I already wrapped it around the tree. And if you look, it's 9 foot 3 inches or 111 inches. So we just found out that our tree is 111 inches around, which is the circumference. We're going to input that into our formula and divide 111 inches by pi, which gives you 35.33. We're going to multiply that by the growth factor of our ash tree, which is, the growth factor is different for every species of tree. We just have to look it up and find what your tree is. So we're going to multiply ours by 5, which gets you 176.66 or 177 years. So we just found out that this tree is 176 years old, which is roughly 1844 or 1845, which is about the same time that James K. Polk became president, the 11th president of the United States of America.
What is the Fibonacci sequence? Simply put, it is a series of numbers where the sum of two adjacent numbers is the next number, starting with 0 and 1. So, 1 and 1, 2, 2 and 1, 3, 3 and 2, 5, 5 and 3, 8, 8 and 5, 13, 8 and 13, 21, and so on and so forth for eternity. Alrighty? You got that? Oh, you don't? Don't care. But how do these numbers relate to nature, though? The origin story for the Fibonacci sequence actually already technically deals with nature. So there was this dude, right? And his name was Fibonacci. Wow, who would have guessed? He wrote this book called Liber Abaci. I think that's how you say it. I don't know. I don't care. But it means Book of Abacus. The book not only introduces the numbers we use today, like 0 through 9, but it also introduces the scenario in which the sequence derives from. So the scenario goes like this. What is the total pair of rabbits if you enclose one pair and they produce another pair every month? Well, I'll tell you. The first pair of rabbits will, have sex. Therefore, they produce another pair of rabbits. So now you have 2 pairs. The next month arrives, and the first pair produces yet another pair of rabbits. Keep in mind that the previous pair of rabbits don't reproduce because they're still newborns, so they can't mingle or do the dirty because that is weird. So now we have a total of 3 pairs. The next month arrives, and the first pair produces yet another pair of rabbits. By now, the second pair of rabbits is now ready to mate, because apparently 1 month is enough for rabbits to consent to other rabbits to touch their no-no square. In total, we have 5 pairs. These steps repeat over and over again as long as no rabbit dies from old age or the malformations from the amount of incest. From this, we have what is known as the Fibonacci sequence. The formula for the sequence is x subscript n equals x subscript n minus 1 plus x subscript n minus 2, where n is the term number. If we plug in 6 into the formula, then we will subtract 1 from 6, which is 5, and 2 from 6, which is 4. Our new equation is now x subscript 6 equals x subscript 5 plus x subscript 4. All this means is just that the 6th term is equal to the 5th term plus the 4th term, which looks about right. The 4th term is 3, and the 5th term is 5, and 3 plus 5 is 8, which is the 6th term.
Math is found in the way we move, how our muscles work, and the forces and torques involved in our movement. For a simple example of the forces acting in our muscles, we can measure torques and find the tension experienced in an arm while holding an object. Torque, a measure of the twisting force causing rotation about an object, is needed for us to perform any movement. Tension is a force developed when a rope, string, or similar object is stretched by another force. It acts along the length of the object opposite to the force applied on it. To find tension, we take the sum of the torques about the shoulder joint so that the tension T can be calculated from T equals 2 weight 1 plus 4 weight 2 divided by the sine of the angle. And if we were to plug in numbers, if this angle is 16 degrees, the weight of the arm 68 newtons, which is about 15 pounds, and the weight in the hand is 45 newtons, about 10 pounds, then the tension would equal 1,145 newtons, which is about 250 pounds. So that's a lot more force the arm is experiencing than the weight it's actually holding. To better understand torque, we can use the example of a bicep curl. The elbow is the axis of rotation, the dumbbell is the force acting on a radius, and the perpendicular distance between the elbow and the dumbbell is the lever arm. As you begin to raise the dumbbell, the amount of torque acting against your bicep increases. This is because the length of the lever arm has increased. However, as you raise the dumbbell past 90 degrees, it becomes easier to lift. This is because the greatest amount of torque is produced at a 90-degree angle.
Hi everyone, my name is James Noble. I'm doing my Math and Nature project on the Fibonacci sequence. The Fibonacci sequence was created by a European mathematician, Leonardo Fibonacci. He came up with the math sequence to understand the breeding of rabbits and to predict the amount of rabbits that could be produced in a certain amount of time. The whole idea of the sequence is each term is the sum of 2 preceding terms. For example, you start from 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and 144. Reason being that 0 plus 1 is obviously 1. 1 plus 1 is obviously 2. 3 plus 5 is 8. 8 plus 13 is 21. 21 plus 34 is 55. 55 plus 89 is 144. The significance of the Fibonacci sequence is its connection to the golden ratio. The golden ratio is 1.618, which is multiplied by this preceding number. The golden ratio's inverse is 0.618. The use of the golden ratio does not work for the first few, but later down the sequence, it definitely does. Which these number patterns follow this Fibonacci sequence.
So, bees. Everybody knows about bees. What do bees make? Honey. But how do we know how much honey is in a beehive? Well, I'll tell you. First, we gotta get dimensions for each of the little cells in the honeycomb. What I got a diameter of 3.44 millimeters. Then you can cut that in half to get one side of each equilateral triangle that makes up a hexagon. Then you can calculate the area of a hexagon, because now you have the side length of them. With this formula, 3 times the square root of 3 times the side value squared divided by 2, and you get 7.69 millimeters squared. Then you need to multiply that area times the depth to get the volume. The depth is going to be 13.42 millimeters. So once you multiply the area times the depth, you get 103.2 millimeters squared, or cubed, which ends up being 0.1032 milliliters, which is actually a unit for volume. Now, we're going to take a sample of honeycomb, theoretically in a 20 by 20 centimeter sample. You first have to find how many cells could fit inside of a square centimeter, and you do that by taking the area that you're converting into millimeters and dividing the area by the area of a square centimeter by the area of a hexagon. You get roughly 13 cells per square centimeter. Then you multiply that times the area of the entire thing, and you get 5,200 cells. And then once you multiply the 5,200 cells by the volume, you end up getting 536.62 milliliters, which is roughly half of a liter of honey.
Hello everyone, my name is Tyler Swallow. Today I'll be going over the freefall formula with you guys. It was thought of by Sir Isaac Newton, and it goes as following. The time it will take an object to hit the earth equals the square root of 2 times the distance over the gravitational force. Now, one thing to keep in mind that's very important is the gravitational force can be different on different places of the earth. So for the sake of these problems, we'll be going with the nominal reading, which is 9.8. So with our first question, we actually have 2 of them. And the first one says, a gopher is gnawing on a tree branch 75 meters from the ground. When he breaks the branch completely, how many seconds will it take the branch to hit the ground from his height? So we'll set up the equation just like this. It is time equals 2 times the distance, which was 75 meters, over 9.8, which was the nominal reading of the gravitational force. And we could simplify that to equal the square root of 150 over 9.8. So if we put that in the calculator, and we will come up with the answer, and it is 3.912. And we will leave it there. We won't grab any of the smaller decimals or run it down. Now our second question, we're not finding the time, we're finding the distance. So we have to switch up our formula a little bit. In order to find the distance instead of the time, it is 1/2 the gravitational force times the time squared. And our question will read, a bird watcher gazing at birds from a distance saw a bird flying with a stick which was dropped. He was able to count the length of time from when the bird dropped it until it hit the ground, which he calculated to be 4.75 seconds. Based on the time, how high up was the stick? So we could set up this formula as distance equals 1/2 gravitational force, which is 9.8, times time squared, which would be 4.75 seconds squared. To further simplify this, it would be 4.9 times 22.562. And when we multiply that together, we get a distance of 110.55 meters. So that's it, folks, and that's how you calculate the distance and time of a falling object.
Hey y'all, my name is Robert Hodges. I'm in Math 172, and I'm going to be presenting my Math and Nature project. I picked out the Fibonacci sequence, and today I'm going to real quickly tell you about it. So this guy on this picture, his name is Leonardo Pisano, I think I'm saying that right. He was born in Pisa, Italy in 1170, and he's the guy who's really credited for the Fibonacci sequence. His father was a merchant, so he traveled with him around the Mediterranean, the Middle East, and Northern Africa, where he got a variety of different educations from Egypt, Syria, and Greece. And whenever he returned home, finally, in about 1200, he spent 25 years of his life writing mathematical manuscripts. And the Fibonacci sequence was found in the Liber Abaci, which he published in 1202. He used a very famous rabbit problem where the rabbits kept multiplying, and so he used that sequence. And the sequence of numbers is 0, 1, 1, 2, 3, 5, 8, 13, 21, where you add you get the product, then you add the 1 next to it. And so I'm going to show you some stuff we see right here, the 5 and that's the circle it makes right there. And this is actually where it's found. I think it's pretty cool. From hurricanes, as we can see, from hurricanes to galaxies to just a shell that you find on the beach. So I found that this was cool. I hope this interests you as well, and thank you guys so much.
Hello, and welcome to my 172 Math and Nature presentation. I have chosen the rule of 72 as my topic for this presentation. And the way the rule of 72 gets its name is from the 72 in its formula, which is 72 over rate of interest, which equals time. I will be using years instead of time for this presentation. Now, if you do not know what rate of interest is when you do a investment such as 500 at 9% annual interest, that 9% will be plugged into this rate of interest, which would be 72 over 9, which would equal 8 years until the 500 turns into 1,000. Here are two problems that go over the rule of 72. For the first one, let's just say Jeff over here, hello, wants to invest $10,000 at 12% annual interest, and he wants to know how long it will take until that $10,000 will turn into $20,000. Luckily for us, the rule of 72 tracks how long it takes until it doubles. So all we would do is we would take 72 and we plug in 12 for rate of interest, and that would give us 6 years. And that's simple as that. And also, for 72, the rule of 72, it doesn't matter how much money you put in. All that matters is the, what's called, annual interest rate, like this. Such as, let's say, Todd here, who is a millionaire, and for some reason doesn't have a personal advisor to do all of this, wants to put $150,586,000 at 6%. And he wants to know how long it will take to double, because he wants to take it out and get a boat. And all you would do is take 72 and divide that by the 6% you get right here, and you will get the amount of years, which is 12 years. Now, remember that the stock market and the investment market is liable to change since it is volatile. So take this as an estimate and not of a sure fact. And that's all I have for right now. So yeah, thank you for listening, if you're even listening to this presentation, and see you.
Hello, my name is Austin, and I did my project on gravity and how it affects our day-to-day lives. And this math problem will be going over how much a person that weighs 100 kilograms on Earth weighs on the moon. So starting off with our base equation, we have the force of gravity equals the universal gravitational constant times mass 1 times mass 2 over radius squared. So the universal gravitational constant for this problem is 6.7 times 10 to the negative 11th power, and as stated, the person weighs 100 kilograms times 7.4 times 10 to the 22nd power, and that is the mass of the moon, over the radius of the moon squared. First, we're going to solve for our numerator, as that will make it easier for us and easier putting in the calculator. So if we put this in the calculator, we get 4.9358 E14. Once we do this, we can put it back into our original equation over 1.74 times 10 to the 6th power squared. And this will give us 163.0268 newtons. To get from newtons to kilograms, you divide by 9.8, and you get 16.6184 kilograms, or 36.637 pounds. So a person that weighs 100 kilograms on Earth will weigh 16.6184 kilograms on the moon.
Let's be honest, how many of us really think about math every day? I promise, unless you're an engineer or a mathematician, you just shake your head at what I just said. But math is way more important than you think. In fact, here's a little idea of what I think the world would look like without math. Oh hey man. Hey dude. Yeah dude, it's so good to see you again, man. We haven't hung out in forever. I'm gonna go out there? Yeah man, come on out. Clearly that sucks. Math is obviously important, and today we'll be talking about one of the most important examples of math in nature, as well as one of the easiest to see: gravity. For consistency's sake, I'm going to use the same example that I gave in my paper. Today we'll be using Newton's law to find gravity. Newton's law is written like this. In this equation, F represents the gravitational force in newtons, G represents the gravitational constant, which we'll talk about in just a second. The two M's represent the masses of two objects, and the R represents the distance between the two objects. G, the gravitational constant, is a constant value that was discovered by Newton to work for finding gravity. Newtons. This is the unit of force. So using an example of a baseball falling to Earth, and plugging in the value for the baseball and the Earth into the gravitational formula with the constant, we get this formula. So this 0.145 is the mass of an average baseball. This absurdly large number is the mass of the Earth. And this 4 down here is given that the ball is 4 meters from the ground. Now that we've plugged everything in, we can just use algebra to solve. Our final answer is 3.612 times 10 to the 12th newtons, which is about 3.6 trillion newtons. This is a unit of force. Thank you for watching my presentation. I hope you have a good day.
Hello, I'm Jared, and this is my project on the probability of change and also the probability in general. So probability can be used in many different aspects: sports, reports, samples, predictions, statistics. Also, insurance is a big one to show the likelihood of certain stuff to happen and how they would pull out the assets. That is also determined by, that could also be in financial analysts, management, and economics jobs. And the equation we're going to be using is PA equals number of outcome over total number of outcomes. So PA will be the total number, and then also the number of outcome is what is the certain thing to come out of, which is above total number of outcomes. 5 curtains, what is the probability of winning 2 out of 5? So it'll be 2 out of 5. And in the history, in the past, there was people that would count cards and go to Vegas, and they would get in groups, and they would just base their winning rate off of reading each other's cards, and they would subtract each other's probabilities and, add them, and also determine mentally, this is how many cards we have left. Okay, so first example is probability of change in gambling, which is a perfect example. 52 total cards we have, and we have 4 of each card. So we have 4 of each suit. That could be spades, aces, diamonds, or anything else. The probability of spades is 4 out of 52, because we have 4 spades, total spades, and 52 cards, and that'll be 1 out of 13. And the probability of drawing for 4 spades will be, very difficult, because it is 1 out of 13. But we have another difficult question. We have a probability of drawing 4 aces in a row. So we have 4 out of 52 cards in total. We draw 1 ace, 4 out of 52, and then we subtract 52 by 1. We get 51. And then the total number of aces cards left is 3. Total number of cards left is 51. And then we go down the line, and we have 2 out of 50. We subtract 51 from 51 and 1 from 3. So we have 2 out of 50 aces, and then we'll go down the line to 1 out of 49, simply. We can convert these into decimals. We have 0.077 times 0.059, and also times 0.040 times 0.020. We get 0.00000, which is 5 zeros, 3634, and we get 4543 over 1.25 billion. Now, there's another example we can use is Monty Hall, and this is a game show host, and he was the person that led Let's Make a Deal. So we had 3 curtains, but I chose, in my example, 5. We have 3 losers and 2 winners. It doesn't matter what the winners are, high or small, but usually they're high and small. So the probability of winning, which we have the high and small wins, is 2 out of 5. And the probability of losing is 3 out of 5, because we have 3 zoinks. But the predicament, though, is that when a person switches their answer, in the nature of probability of change, that the numbers, the numerators, switch, because the other curtain is shown and it's a loser, so that means it will be a more likely chance of getting a winner. So you will have a 3 out of 5 chance of winning and a 2 out of 5 chance of losing. And that is how probability and probability of change is simply put. Thank you.
Hello, my name is Sebastian Yang, and I'm going to be talking about how the rate of change can be applied to fishing. So in the word problem here, it says Mr. Rogers and Mr. Walls decided to go to Fort Caswell to catch some fish, but instead Mr. Rogers wanted to compete with Mr. Walls in a fishing contest to see who can catch the most fish within the whole day. Mr. Rogers fished between 6 a.m. to 12 a.m. while Mr. Walls fished between 1 p.m. to 7 p.m. Mr. Rogers wanted to keep track on how many fish they caught during their time period in the charts below. There's Mr. Rogers' chart on how many fish he caught, and here's Mr. Walls' chart on how many fish he caught. So in the question here it says, what time will the rate of fish increase? So in the chart here for Mr. Rogers, we can say that around 6 to 8 p.m. The fish increases from 5 to 9 fishes, or the amount of fishes he caught by then. And as for Mr. Walls, he has made an increase of 2 fishes between the past 3 hours. So we can cross out B and C, D, because they're a bit too long for the amount. And so now it's between A and C. Let's see. So it can be A because, like, for this part, for Mr. Wall's part, it says 1 to 5 p.m. But in the chart here, around 4 to 5 p.m., there's a decrease of 1 fish per hour. So we can cross out A, meaning that C is the right answer.